Hi guys, it's Kate, and this is the first video for week 12 of Math 23B. We're in the final stretch. Here we go. First off the bat, we want to start with a proof of Stokes Theorem, and we're not going to be doing one that necessarily goes through every single detail, but the one that we will be focusing on in class is going to go through the major steps of this theorem in an informal, not quite as rigorous way. The complete theorem itself is actually in the appendix of the textbook. You're more than welcome to take a look at it, but once you do, you'll see exactly why we can't quite devote as much class time as we'd like to it, but there are a few major steps involved in the proof that are absolutely accessible, worth our time and our understanding as we proceed through understanding exactly what this major theorem says. So what we're doing is that in the limit of a very small parallelogram, Stokes' theorem is basically made true by the definition of the exterior derivative. So Stokes' theorem itself, which is the following, and we can see that the exterior derivative is critical to this theorem. Now the proof of this theorem basically consists of showing that nothing goes wrong when we integrate over a large region X by subdividing it into many small parallelograms. So that's basically our first step. We want to break up X into a lot of small oriented k+1 parallelograms. And then when we're looking to compute the right-hand side here, the integral of the exterior derivative over X, instead what we want to do is we want to evaluate a sum of the exterior derivative over a bunch of parallelograms. When they're added together, they will equal X. But there is an error here. It's basically proportional to the maximum oscillation of the exterior derivative over a parallelogram, which is going to go to 0 as the parallelograms get smaller and smaller and smaller in the limit, because phi, our form, is C2. Now, our next step, instead of saying, okay, instead of thinking about X, consider an enormous number of k+1 parallelograms, we're now going to apply the definition of the exterior derivative for each small parallelogram. So we've gone from here, where we're integrating the exterior derivative over this entire region, to summing the value of the exterior derivative, and that should be a bold D, over a bunch of k+1 parallelograms, because altogether the k+1 parallelograms make up the entire region X. Now we're going to apply the definition of what it means to evaluate the exterior derivative over all of these k+1 parallelograms, and that, of course, by the definition of the derivative, is over each of these parallelograms, we actually want to be integrating phi itself over its boundary. And of course, there's an error there also, because the definition of the derivative applies only as a limiting case, but it does go to 0, so there will be like a little bit of, this is technically an approximation, until we take a limit. It goes to 0 in the limit of small parallelograms. Now, when we do that, when we actually evaluate this integral over the boundary of each of these tiny parallelograms, all the integrals over the internal boundaries cancel out. And you can think of it, imagine you have two neighboring parallelograms in this that make up this region X, like just two of them of the many, many, many that you're using. And they lie next to each other like this. Now, if we talk about normal counterclockwise orientation of their boundaries, the one on the left is going to be oriented as follows. And the one on the right is going to be oriented like this. And we see that this interior boundary is shared by both parallelograms and is traversed once in either direction when computing the sum of these integrals. And so it is actually going to cancel itself out when you compute it as part of evaluating phi over the boundary of the red parallelogram. And then once you add on computing phi over the boundary of the blue parallelogram, because the red one, you're traveling up, the blue one, you're traveling down, it's going to cancel and actually not contribute at all to the final sum that you will get. And this happens no matter what, because the basis vector that is not tangent to the boundary points out of one parallelogram and into the other. So you know that on any interior boundary side of these parallelograms that are shared with another parallelogram, if all these parallelograms are oriented the same way, the internal boundary contributions will cancel out, because whatever they contribute to one parallelogram, they contribute the exact opposite sign to another. The last sort of problem that remains that makes this a bit of an approximation is best summed up by this example. Say that the total region X that we started with is bounded by a diagonal line, and we use dyadic decomposition into squares, right? So we're trying to approximate a diagonal line by using squares, the diagonal boundary of a region. So it looks something like this. So imagine that this is the boundary of X, maybe what's over here is X, and so we are trying to break down all of X into these little dyadic squares, but note that our boundary of the squares goes like this instead of being a nice diagonal line. But of course, the total length of the boundary of the squares is always, always going to exceed the length of the diagonal line, no matter how finely you make the dyadic decomposition. While we're not going to go into a great level of detail about how this is handled, the full proof in the appendix will show you exactly how to deal with this fact and how you can eventually believe that this equality up here, our original statement of Stokes' theorem, is in fact true. Stokes' theorem shows up everywhere, and before differential forms were a lens through which we could study calculus, to look at this unified body of theorems, each of these separate theorems themselves in different dimensional spaces were discovered. So let's take a look at them. The first one is Stokes' theorem in the plane. That's called Green's theorem. And Green's theorem is when you're in R2, and the setup is that you have a region known as S, and it is bounded by an oriented boundary C. And it basically tells you that if you adopt the convention that the curl of a vector field in R2 is this particular function, Green's theorem tells you you have a choice. Given this particular vector field, this region S, its oriented boundary C, you can choose either to compute the line integral or the work form of F around that boundary curve C, or you can compute the curl of F over the entire region S. In classical vector calculus, the name Stokes' theorem is specifically given to the case where a one-form phi is integrated around a closed curve in R3. So let's take a look at that. We are given that we have S, which is an oriented surface, and C is the boundary curve. I usually draw this using a hemisphere. A setup would be one like so. Imagine C being the equator and S being the northern hemisphere. And we basically have a choice here. We can either choose to integrate phi over C. So that is going to be a line integral in the sort of vector calculus notation. Or we can choose to integrate d phi over S, the entire surface. If we choose to introduce vector fields, which is usually what happens when you're in a more applied course like 21A, or when you encounter this in something like physics, you'll note that phi is actually written as the work form of a vector field. And so then the derivative of the work form is the flux form of the curl. So here you have a choice between computing the work form of a vector field around the curve C or the flux form of the curl of F through the surface S. The way that is usually done is that we take the dot product of that vector field with a tangent vector when you're doing the right-hand side here around C. To integrate the curl, we take the dot product of the curl with the normal vector. Let me draw one on here. A normal vector, of course, written in terms of the parametrization of the surface, S. And the resulting rewrite of Stokes' theorem looks something like this. Now, unfortunately, we've sort of swapped. What was on the right-hand side is now on the left-hand side down here. What was on the left-hand side is now on the right-hand side down here. But to compute this integral on the right-hand side, we take F and dot it with a tangent vector, of course, all in terms of the parametrization. We take the curl of F and dot it with the normal vector. I've drawn one on here, all in terms of the parametrization as well. This should be named S instead of X, sorry, to keep our names straight. Last but not least, we have the divergence theorem. That's the name used in the case where a two-form phi is integrated over a closed surface in R3. So instead of having a surface with a boundary curve, like we had up here for Stokes' theorem, what we have is a solid with a boundary surface. Sort of like the egg with the eggshell kind of idea. So if X is an oriented domain in R3 whose oriented boundary is S, so X here is the solid, S here is the boundary surface, we have a choice. We can either compute phi over the surface or integrate phi over the surface, or d phi over x. Now to introduce vector fields, what we end up doing is we write phi as the flux form of a vector field f, and then the derivative of the flux form of f is the mass form of the divergence of f, just as you found from, I think that was proof 24.2. And again, to integrate the curl, we take its dot product with the normal vector, that's over the surface there. The resulting rewrite of Stokes' theorem ends up looking like this. This is something you might see in Stewart's calculus. So again, these have swapped sides. This surface integral is the vector field f dotted with the normal vector. Note this is different from this surface integral that we were looking at up here. This had the curl of f, this was f itself. Then over here we integrate the divergence of f over the entire solid, known as x. So these are these sort of applied versions of Stokes' theorem that happen in particular dimensional settings that you may have already run into if you took a more applied version of multivariable calculus, or if you've gone into physics already and seen this before. Certainly shows up in 15b, electricity and magnetism, but will come up again and again and again, especially if you're going into engineering or anything like that. Very important stuff.